In this video, we'll be discussing the critical path algorithm for solving task processor problems. And here we'll just be focusing on how to find the critical path. What does it mean? And in later videos, we'll actually be practice using it. But for now, it takes a bit of time to actually figure that out. That's what we'll focus for first. So before we get into anything, what is a critical path? A critical path in a task processor problem is just the longest path in the entire diagraph. And basically, it's helpful thing to know because it gives us a minimum time of completion for the overall project. And to show you what I mean, I think it will be helpful. Let's look at an example of finding a critical path. And I'm not going to show you how to find it in this video. I'm just going to give you the right answer and kind of discuss what that means as we're looking at it. But to reiterate, the critical path is the longest path on the entire graph, and it should go from the start all the way to the finish. Okay, longest. I'll just go ahead and fill that in the packet. But basically, let's start off with a new fresh example. So let's say that this digraph represents the tasks that it requires to put together a dresser that you may have bought at IKEA. So if you've ever purchased furniture or something from a store like IKEA, a lot of times it comes in like a cardboard box, like it has not been pre-assembled. You have to do a lot of the assembly yourself. And if you look at the diagrams or the step-by-step instructions, there's like 50 steps. There's a million things that we want to do in order to make sure we put this together properly. And if we don't follow the right set of steps, it gets messed up, and then we just lost all our money. But basically, let's just imagine that these are and why this would be useful for the manufacturer is in writing a set of instructions for the user, we could try to figure out what would be the fastest way that the user could actually assemble this dresser. And of course, certain things have to happen before other things can happen. So let's just pretend that all of these tasks stand for something like this. And actually, this is an example that is from the book as well. I just am changing the context to something a little bit more, well, whatever, fun, whatever, in my opinion, just kind of illustrating to illustrate another use of these algorithms. But anyways, if I want to know what is the critical path, one of the difficulties of finding it is notice that there are so many different paths that we could traverse from start to finish. And remember, a path is just a set of distinct adjacent edges, and it would be a path that goes all the way from the start to the end. But if we wanted to know how many different ones there would be, well, my guess is there's probably 20 or 30, but there's a lot of different options, so how do we know? But what I'm going to do is I'm just going to give you the critical path, and in the next video we'll talk about actually finding it. But the critical path in this digraph, maybe some of you have already been able to try to find it, actually goes through these vertices exactly like this. And if you're wondering how did I know that, well, I've done this problem many times before, but I just wanted to give you the answer first and kind of show you how do we find this in retrospect, which is something that we call the backflow algorithm. But anyways, if I'm looking at this particular path, notice I could find the length of the path by adding up all the times of the tasks in that entire chain. So I have task AP, 7 hours. Hours doesn't make sense. Let's say minutes is how long it takes to assemble each of these tasks for that dresser. So 7 minutes plus 5 minutes plus 7 minutes is 19. Plus 4 is 23, plus 4 is 27, plus 1 is 28, plus 6 is 34. So the total time for that path is 34 minutes. And that's the critical path because it's the longest one you can find. So you could look at a bunch of other ones, and you could do it just by guess and check. Look at other various paths to see, can I find one that is longer? But you will not be able to because that is the critical path for this graph. So the critical time, we could list, the critical time is always just the amount of time it takes, so 34 minutes. And the critical path we could list much like we'd list a path or a circuit from a prior chapter. So I could say AP, comma, IF, comma, IW, comma, IP, comma, HU. Notice this is not a priority list, but just a list of the critical path itself. Then IC and FW. Oh, sorry, I'm putting this in the wrong spot. This should all be this should be for the entire project, 34 minutes. And then the path is AP to IC. Okay, but like additionally, besides finding the critical path of the whole project, you can also find a critical path and a critical time for an individual point on the graph instead, which is a lot easier because this is a very large graph. It's hard to find the largest of all possible options without having a specific strategy. So let me go ahead and erase this because it's wrong. But let's just discuss, what if we wanted to find it for a specific point? Like this example from the packet asks, what is the critical time and path from the vertex HU? So shifting my focus, and I'm gonna switch to purple instead of red now. But the thing would be, from here, what would be the longest path to the end? So instead of looking at the whole project, I'd be focusing on, well, in this little part of the diagraph, what's the longest available path from there? This is a little bit easier because there's way less options. From the start, there was 20, 30, whatever different paths. But from here, we only have 1, 2, 3 paths from HU to the end. And the critical path is just going to be the longest. So we could figure this out just by attrition by looking at them all. Like if I imagine the top chain, that would be HU to IC to FW. That critical time would be the sum of all the numbers, 11. If I was to look at this path, HU to PD to the end, that's only 7. And if I was to look at this one, HU to EU to the end, that's only 6. So basically, I know that the top is critical because it's the longest, and it's a lot easier to do when there's less options. So the critical time for HU is 11 minutes. And that would be the critical path for the vertex HU would be HU to IC to FW. And it's a lot easier. But notice that on the critical path for the whole project, that same critical path for that vertex was in it, which is, it's not actually guaranteed to have every critical path, but it's a pattern of, if I want to know what's going to take the longest overall, it typically will involve the longest individual chains. And the way that we can find the critical path for the entire project is by working our way backwards, seeing like, what's the critical path of this? What's the critical path of this? And if we solve them all, it will become a lot easier to find the total project, kind of as a sum of all the individualized critical paths. But before we get into that, that's what's called the backflow algorithm. I just wanted to analyze, okay, what's the point of all this? Why do we care about critical times and critical paths? And the reason is the critical time gives us a minimum time of completion for the project as a whole. Like if I was to look at this red critical path, basically what it implies is that there's a unavoidable series of tasks that follow this particular order, and it's impossible to complete this project, so I can't put this the rest are together in any shorter of a time than 34 minutes. Because in order to complete the project, I need to first do this. Then I'll need to do this. Then I'll need to do this. I'll need to do IP, HU. This order cannot be broken because each one of those tasks relies on the previous to be completed. And the critical path is the longest such path, meaning that, so there's a bunch of other tasks that we also need to do besides just the critical path. But on the critical path, since it's the longest one, it's the longest chain of events, and it's impossible to do it any faster. So what we could imagine is, let's say we had 2 workers. So let's say me and my buddy are going to be putting this dresser together. Let's say that I decided to do the critical path and I have him do the rest of the tasks. We could imagine that would be a pretty decent arrangement because there's other tasks we could kind of fit in outside of the critical path. It still is not necessarily, we're not necessarily guaranteed to finish this project in the critical time, but it's impossible to do it any shorter. So let's say that I asked you guys, can I complete this project in 30 minutes? No, it's impossible because of the critical path. And it turns out it's also helpful to use the critical times to actually schedule and develop a priority list, which is what we call a critical time priority list. Very, very helpful to know, which is really the point of why we're getting into this. But the critical path is helpful to know. And if I wanted to know the critical time for an individual vertex, it gives us the minimum time of completion from this point forward. It's going to take us at least 11 minutes to finish once I'm at this step. And each task would be the same. Each individual critical time tells us exactly that. In the next video, we will find the critical path, and I'll show you how you actually find it, because here I just gave you the answer and didn't tell you how I knew. But we'll do that in the next one. See you next time.